Exactly. Okay, you started recording. Okay, you have 1 minute and then you can start, please.
Okay.
Okay, we're just waiting for Rishi to come back with his water.
So before you start, how were you guys able to do senior design 2 with COVID going on?
By getting a very, very quick head start, speaking to everybody we needed to very, very early in the semester, and doing a whole lot of extra work on our own on the side.
Yeah, we did a lot of work over the summer.
Yeah.
Okay, thank you.
If you have more questions about that, we can answer them later on after the presentation. Professor, we ready to start?
Yes, you can start right now. Thank you.
Okay.
Let me just verify that that's working. Cool.
In that case, good morning, everybody. Thank you for attending. My name is Robert Walsh, and I'm accompanied by
Chloe Rentzel.
Peter Mowen.
And Rishi Dutt.
We're a senior design team D03. Our advisor is Dr. Sarai, and our coordinator is Dr. Harabi. The use of electric vehicles is becoming more common every day, but as that increases, so does their exposure to their batteries for damage or potential damage. Proper simulations are needed to accurately predict the behavior of these batteries under various types of abuse. But since the lithium-ion batteries are incredibly complex, these simulations can be very costly. The solution is to develop accurate homogeneous models of the batteries to simplify these simulations. In order to achieve this, the battery characteristics must be experimentally obtained, but are limited by current processes. Current UTMs are not made for long-term cycling tests, so there is a gap in obtainable data at present. Creating a system to obtain this data would contribute to safer electric vehicle design and can be seen in UN Goals 7 and 13 for affordable and clean energy, as well as climate action, respectively. In order to develop an appropriate system, we needed to fit a few guidelines. First, we need to fit within our environmental chamber of our lab. We needed to apply up to a 20 kilonewton load, remain quasi-static, which is to say it has a displacement of no more than 1 to 2 millimeters per minute, be able to operate within a negative 10 to 40 degrees Celsius range, lock the punch head at various heights, and record force, displacement, voltage, time, and temperature of the experiment.
So these were our three potential solutions for applying the force to the surface of the battery. We researched rack and pinion, power screw, and universal testing machine designs. And these were our main considerations when analyzing each design. We chose to move forward with the simple UTM design due to the fact that it met all of our requirements, especially the dimensional requirement. So our solution is an electromechanical system that translates the rotational motion of a motor to linear motion of a punch head. We used a series of gears to decrease the angular speed while increasing the torque. And the gear train is attached to a pair of power screws, which translate a crossbeam up and down to apply load to a battery cell. And now I'll pass it off to Rob, who will outline our system and component analysis scripts.
Here we can see a high-level overview of what our system is actually capable of. We provide the system with a system displacement or load, experiment runtime, and an environmental temperature in which it will operate within, while we obtain from it the load and deformation, voltage, and temperature readings of the battery. The main design considerations we had to focus on were the optimization of the DC motor and powertrain combination, designing of the mechanical structure, designing of the electrical subsystems, and development of both the firmware and the software. With the first bullet point on the screen, we had a bit of a chicken the egg situation develop. From the electrical side of things, we needed to know, in order to pick out the motor, we needed to know what torque and RPM the gears would be running at. However, from the mechanical side, we needed to know what, in order to pick the gears and power screws, we needed to know what the torque and RPM the motor would be supplied. In order to solve this problem, we developed two different MATLAB scripts. The first of which is the DC motor analysis script, which takes the physical characteristics of the motor, such as nominal voltage, and provides performance graphs at three different temperatures: the minimum, the maximum, and room temp. .mat files are created and then passed to the system viability script, which Chloe can elaborate on.
Thanks, Rob. Based on the previously described chicken and egg scenario, we needed to select components that optimize factors of safety, displacement rate, and motor torque and RPM. The following slides will explain the calculations performed by the system viability MATLAB script. Optimization of the power screw focused on the self-locking capability and a required torque range. The self-locking capability was dependent on the coefficient of friction and the lead angle. The torque range is dependent on the range of the minimum torque required to apply the maximum load and the maximum torque the lead screw can handle without breaking. This range of values allows us to optimize the factor of safety for the power screws. Our next stage relied on the calculation of the gear factor of safety in relation to the amount of force it could be subjected to. This was completed by referencing the manufacturer's equation for maximum load that the gear teeth can withstand and using Shigley's mechanical design to find the actual force on the gear teeth for our application. From these, we were able to calculate the factors of safety on all gears by comparing the actual and maximum tooth loads. Similar to the gear teeth factor of safety, we needed to calculate the factor of safety in relation to the torque. This was completed by calculating the maximum allowable torque as a function of the maximum load and pitch diameter. The factor of safety was then calculated using that maximum torque and the gear's actual torque. An example output of the previously described script is provided. This displays a different motor in each column and provides displacement rates, factors of safety, and more, depending on the motor, gear train, and power screw being tested. So after we nailed down the DC motor, gears, and power screw combination, the bearing and shaft calculations could be started. By performing a static analysis of the shafts, the reaction forces of the bearings were calculated. Diagrams of the moment could then be graphed for each of the shafts. This information is critical to examine stress concentrations on the shaft, including steps and keyways. The moment at any point on the shaft is the magnitude of the moments in the X, Y, and XZ planes. Using this calculation, we can determine the von Mises stress and stress concentration values to calculate the factors of safety for all the shafts. Since our team decided to use helical gears, they introduced an axial force on the shaft. To counteract this force, combined bearings were selected for shafts subjected to significant axial force. We also ensured that all the bearings operated well within our required temperature range. To calculate the factor of safety of all the bearings, the dynamic load ratings from the manufacturer were compared to the ideal dynamic rating required, which is dependent on the force and bearing specifications. Once the bearings and shafts were selected and designed, the structure went through its preliminary design stages. Initially, most of the components were made of aluminum 6061 to reduce cost and weight of the structure. Through SolidWorks simulations, this design proved to be adequate to handle the loads it was subjected to, having a max deflection of 0.26 millimeters. However, by using design thinking, the goal was to minimize the maximum deflection. After many iterations, the maximum deflection was reduced to 0.066 millimeters. This was accomplished by redesigning the supports and changing the material of the components with the largest amount of deflection to low carbon steel, which has a higher yield strength than aluminum 6061. Now I'm going to pass it off to Pete to discuss the electrical side of our project.
Thanks, Chloe. So as you can see here, we've got a block diagram of the electrical subsystems. The brains of the electronics package is an Arduino Nano, which receives various data from other systems and uses that data to control a DC motor. It also sends that bit data back to a human-machine interface, which stores it for later analysis. The human-machine interface, or HMI, is a program running on a separate computer that collects data and also controls the device by sending commands to the Arduino Nano. For this presentation, we're going to focus on the force displacement and DC motor systems, as well as the human-machine interface, as those are the critical components for controlling the device. At the heart of the force measurement subsystem is a 19.6 kilonewton load cell, which when compressed, creates a differential voltage on its output line, which the load cell amplifier then converts to a number, which it passes up to the Arduino Nano, and the Arduino converts that number into a force reading using software. There was already an existing software library for the HX711. However, it used a programming technique where it would block the processor while it was waiting for the load cell amplifier to send data, which wouldn't really work in our design. So we decided to update this software library to work with hardware interrupts so that the Arduino Nano could service other subsystems like collect voltage and temperature data while waiting for the load cell amplifier to have data ready. To test the force measurement subsystem, we ran a compression test using the Instron universal testing machine on the first floor of the engineering building, where we compressed the load cell to these various calibration points and held it at that point for 1 minute while recording the instron reading and the readings from our load cell. And then we compared the readings using a % error, where we assumed the instron reading was the correct value. And our force measurement subsystem was within 1% of the instron reading, so we considered this subsystem passed. For the displacement measurement system, we decided to go with a pair of off-the-shelf digital calipers that have a USB serial out. The top jaw of the calipers is fixed to the device, and the bottom jaw is allowed to move with the crossbeam. So as the crossbeam moves, new displacement data is sent out over this USB wire at 1.5 volts. It runs through an amplifier circuit to bump it up to the 5 volts that the Arduino Nano needs to be able to read it. And the Arduino Nano then converts the received data to a measurement. So there wasn't really a software library for this particular piece of hardware. We did find a sketch online that somebody had written to read data from a digital caliper. However, it wasn't a fully fleshed out library. So we took that sketch and turned it into a library that supports hardware interrupts. To test the digital calipers, we actually just connected them to our system, and this was also a test of our constant displacement experiment. We told the machine to displace to a value of 1 millimeter, and the graph that you see here is the results from our first trial, where it did get to 1 millimeter and was within the accuracy of the calipers of 0.1 millimeters plus or minus 0.3 millimeters. So all of our data points were within that range. And for the other trials we ran, this is also what we saw. So we considered this subsystem passed as well. For the motor subsystem, we chose a 24-volt DC motor with a 60-to-1 gearbox on it, which outputs to the mechanical subsystem to move the punch head and apply load to the surface of the battery. The motor is connected to a DC motor driver, which receives control signals from the Arduino Nano, including a pulse width modulated signal to control the speed of the motor, as well as 2 control signals to tell the motor to go forward or backwards. For this piece of hardware, we also ended up writing our own software library, which used one of the hardware timers on the Arduino Nano to control the pulse width modulation. So we ended up writing our own piece of software for this, even though the Arduino library has a PWM function. However, that function doesn't work at the frequencies we needed for this motor driver. So to test the DC motor, we fixed the motor in place and attached a wheel to it that had a hole in it. As the wheel spins, it passes through this optocouple, and when the hole passes through the optocouple, that sends a pulse to the Arduino, and the Arduino counts those pulses. So we let this run for half an hour to measure the average RPM, which we saw was about 105 to 106, which was outside the range of the datasheet of 83 RPM, plus or minus 15%. And we also noticed that the no load current, while it was within the datasheet value of less than or equal to 60 milliamps, it was much lower than what we were anticipating. However, when we used these values in our DC motor analysis script and system viability script, it looked like the motor should still work, so we considered this passed as well. So each of those subsystems is tied together with some control logic that runs on the Arduino. So on the screen, you can see a finite state machine that outlines the control logic with the transitions between the states left off for clarity. So at startup, the device waits for the human-machine interface to make contact. It then sets up all those, it sets up software objects that represent all those pieces of hardware. It runs a movement test where it just moves the punch head up and down to make sure that that works. And then it waits for a command. So the HMI could send it, could tell it to do one of 2 different experiments. It would run that experiment and then go back to the waiting command. If in any state the HMI tells it to stop, the program just goes back to waiting for a command. So speaking of the HMI, I'm going to pass this off to Rishi, as he was the lead developer on that portion of the project.
Thanks, Pete. So when we boot up into the HMI, we're greeted with a setup window we can see to the left of the screen. So that establishes a connection with the Arduino. We can choose which serial port the Arduino is connected to. And then when the connect button is pressed, the HMI sends the string Marco1 and expects to receive Polo1 as a handshake message. So from there, we can head into the main menu, which allows the user to jog the punch head up or down in preset increments. The user can also start various experiments, but before they do, they have to firstly set the directory to which the raw data will be saved, and secondly, the two experiment parameters. The first one being time, and the second being either maximum force or maximum displacement. Once these conditions have been met, the user can start an experiment, and the experiment window has readouts and graphs of force, displacement, voltage, and battery temperature. So if the experiment concludes without error, the user may close the program or run another experiment. However, if there is an emergency, the user can press the big red e-stop button to the top left, which just commands the Arduino to stop the motor. And then the user can enter the debug window, which you see to your right, to monitor any incoming messages from the Arduino, as well as send commands to help diagnose the issue. So now we will conduct a short demo of our system.
So this sped up video begins by pressing the experiment start button, at which time the punch head lowers to try to find the surface of the battery by looking for a measurable difference in force. Once achieving that, it pauses for a few seconds and then begins the actual experiment by lowering the punch head to the desired depth, which is 1 millimeter in this case. The system will then wait for the duration of the experiment. At the conclusion of the experiment, the punch head will retract back to the initial position. It should be noted that the jumps that we're seeing on the displacement graph, which is seen in the middle of your screen, are actually meant for troubleshooting and programming purposes and are not present in the final product. At the conclusion of the experiment, the user is then prompted to either run another experiment or to quit the program altogether.
So now that we've demonstrated that the machine does work, let's take a look at a particularly interesting trial that we performed. So in this trial, we wanted to see if our system would go to its max load. And as you can see in the force versus time graph on the right, after about 7 minutes, we did hit 19.6 kilonewtons, which is just under this 20,000 newtons line. So we achieved that goal. However, if you look at the displacement versus time, it's not quite linear. It is close to 1 millimeter per minute, but it's not linear. So let's talk about that for a sec. So as you can see in this table, as time goes on, force is also increasing, but displacement rate is decreasing. This is because for this trial, we just had the motor set to run at 100% for the whole trial. So that was motor top speed for the whole thing. Also, the 24-volt motor that we picked out is expected to run at about 0.65 millimeters per minute at the 19.6 kilonewton load. That's kind of far off from the 0.9 millimeters per minute that we observed. And when we went back and looked at our system viability script, we found one of our assumptions was in error. We did not take into account the efficiency of the gear train, so it was assumed to be 100%. So that's why our actual displacement rate is pretty far off of our measured one.
So if we revisit the original metrics that we were comparing the system against, we can see that we did indeed we were able to achieve the dimensional requirement of being able to fit within the environmental chamber. We can achieve the force limit of up to 20 kilonewtons. We can lock off the punch head at various heights, and we can log force, displacement, voltage, temperature, and time of the experiment. Now, our displacement rate, even though it is still quasi-static, is not constant, but that will be updated in future software updates. And as for our temperature range, we can operate within the positive side of the temperature range from 0 to 40 degrees Celsius, but additional experiments need to occur at -10 degrees Celsius.
So the total cost of our project is a little over $2,000, and we realize that this is a rather expensive build. So it should be noted that the funding past normal $1,000 limit was generously provided from Temple's own electrical vehicle safety lab. And from this cost breakdown, we can see that the majority of our budget was spent on building the main structure and the gear train. However, significant work was done on both the mechanical and the electrical side to reduce the financial burden. So early iterations of our design required a gear train that was well above the $2,000 range, along with a $400 LVDT module for the displacement measurement subsystem. The mechanical team was able to reduce the cost of the gear train to below $1,000 through several design iterations, and Pete was able to minimize costs further by replacing the LVDT module with a simple pair of digital calipers. So eventually our team was able to bring down the total cost from the $4,000 range to just over $2,000, which we're very happy with. The timeline, however, is a slightly different matter. So our original plan was to start work on the main build and the software in tandem after the electrical components were tested. However, we quickly realized that this would not be feasible as testing software required a physical model. And unfortunately, completion of the main structure was pushed back by 2 weeks, mostly due to machining issues. But this 2-week delay in completing our prototype pushed back software development by almost a month. But we were able to fully assemble the main structure and install the electrical hardware by November 13th, and we integrated the firmware and the HMI between the 14th and the 19th. And now Chloe will speak on future development of our project.
Looking back on the lessons we've learned, there are numerous developments which would improve the project. First, we would want to maintain a constant displacement rate by implementing a linear regression into the code to monitor the speed of the motor. Also, we would like to develop more robust safety checks. Mainly, we would want to develop a stop criterion for when the motor stalls. Lastly, we would buy a more powerful motor, which takes into account the efficiency of the gear chain. Thank you to everyone for attending. We would especially like to thank the Electric Vehicle Safety Lab for the contributions, and Dr. Sarai, who was our advisor, and Dr. Riggio and Dr. Haravi, who were our coordinators, for all the feedback and support over the past year. At this time, we would like to open the floor for any questions.
Okay, thank you very much, guys. Is there any question from participants? And I should mention that we have around about 65 participants, a very large one.
Oh man, I'm glad I had my video thing closed the whole time.
Okay. Any question?
How is the battery actually like held in place when you're testing it? It goes on that bottom plate there, right?
It does. So the battery is actually meant to have a mostly free form. We don't want to keep it too rigid because as the actual test is occurring, there could be slight changes in the structure of the battery. So it doesn't want to. We don't want to hold it down incredibly tightly. The terminals of the battery are held in the black pieces you see at the end, which is where the terminals will go. So we can measure the electrical response of the battery. But the rest of the battery is more or less free to move slightly as it deforms.
Okay, very cool. Thanks.
It looks like we have a question in the chat. Meme says, with the motor having close to 20% error in your testing, how was it that you considered that requirement passed? Pete, you want to take that one?
Yeah. So when we put the measured values back into our DC motor analysis and system viability script, it still looked like the system would work based on those projections.
And that's based on RPMs, factors of safety, things of that nature.
Yeah.
And somebody else was about to ask a question when I read that. I'm
yeah,
sorry.
yeah, Rob. Back to the battery being able to move freely. Do you think that in any way that could have affected your results and data at all?
So the testing that we did was actually not on a lithium-ion battery because we have a limited supply of those, and we want to retain those for experiments to match the research that the Electric Vehicle Safety Lab is conducting. The tests that we performed were actually using a polymer shooting target with a piece of aluminum on top to increase the overall resistance and therefore get a more measurable graph. So there were no lithium-ion batteries done at this point in time. I will say the polymer target did a fairly decent job of representing similar types of material and allowing flow. It could have skewed our results slightly, but at this point in time, just due to the force displacement curves that we were seeing, we would consider that to be a negligible difference.
Thanks.
Any other question? Okay, so it seems that you're done, guys. Thank you very much for your presentation.
Thank you very much for your attendance.
Thank you.
Appreciate it, guys.
Thank you.
Thank you, guys.
That was amazing, guys. Have a good day.
Thanks, Carly.
Thank
too.
you so much. You guys
Really
are the
good
best audience.
presentation, guys.
Thank you so much.
Thanks, Dr. Riggio.
Thanks.
Bye.
See
Have
ya.
a good evening.
Bye.
Yeah.
Bye, guys. Bye. Thank you.
Thank you very much for your hard work. Have a great day. Bye-bye.
Thank you.
Thank you.
Thank you.